Hello again, organic students. Let's talk about oxidizing agents. I'm going to go back to the notes. Wrong. Let's just stop altogether. Okay, there we go. All right. Before we talked about oxidizing agents that had an oxygen-oxygen bond in it, we're going to talk today about oxygen-metal bonds. And let's start with chromium. Now, if you'll notice, chromium has a lot of reagents right here, but the key is it is in its chromium plus 6 oxidation state, and it is very, very effective, by the way. Yes, we have used it in lab. We use something called Jones reagent. All right, so strong. Okay, the chromiums tend to be very strong, and they are not very selective. And we're going to see them pretty much in three ways. The first way is just chromic acid, and that is right here. And so if you ever see CrO3 in H2SO4, that is the same thing as H2CrO4. So basically you are creating chromic acid, which is exceptionally strong. Now another one is sodium dichromate, or it could be potassium. So it's Na2Cr2O7, okay? And that generally is also used in acid. Or of course it could be potassium. And that one is also very strong. And then of course there's the Jones reagent, and the only difference is this one would be acetone. Where do we put that? All right, so all of those are particularly strong, and then you would choose one over the other just based on your needs. Okay, this one at least is in acetone. The other two are polar protic. Now, we don't want to go completely to carboxylic acids all the time. So remember, strong oxidizing agent will take you as far as you can, all the way up to a carboxylic acid. And sometimes it'll take that last one and cleave it off and make it into a carbon dioxide. So we don't want always to be able to do that. So we need something a little bit more selective. And there is two: pyridinium chlorochromate, also known as PCC, and the Swern reagent. I, of course, use PCC most often because that's the one I learned with. All right, what in the world is PCC? Basically, and this is a jolly term, I call it a poisoned, if you will, a poisoned oxidizing agent. So it will stop at the aldehyde stage. It'll stop at the aldehyde stage. Okay, let's see what all of these will do. So let's start with our primary alcohols. All right, the primary alcohols, if you use the strong ones, they're going to go all the way to carboxylic acids. There's no way to stop that. You can't say, ooh, I'll use 1 mole of my chromic acid. Okay, there's just no way to stop that. If you're going to use a strong oxidizing agent, you get what you get. So if you want to stop, you are going to use the PCC. And so this is the selective. And every time I say PCC, the Swern fits in here. It's just the one that I use most often. Let's go over to the whiteboard. All right, let's take a look at PCC and pyridinium chlorochromate. I was just thinking, should I draw it for you? It's probably not important, so we'll just keep calling it PCC. All right, so let's take a look at primary alcohols. I could use any one of those reagents, okay? So I'm going to generically put it like this, and it is going to convert it to a carboxylic acid. Or if you start with an aldehyde, remember that's only a halfway step, it's also going to go to a carboxylic acid. And so that is any of those CrO3 or sodium dichromate. Okay, and then this could be an acetone, it could be in sulfuric acid, but any of those strong reagents will do that. If you want to be selective, you will actually stop at the aldehyde stage and or the Swern reagent. Now, the beautiful thing about PCC, it won't touch carbon-carbon double bonds. So sometimes you can use this expensive reagent and not touch double bonds. So for instance, let's say you had that. Okay. And you only wanted that one to react. How could you go and selectively choose the alcohol over the alkene? PCC happens to be one of those ways. So that's another benefit of your PCC. All right, that's your primary alcohols. Let's take a look at your secondary alcohols. Now, the nice thing about this is, hey, it stops at a ketone, end of statement. Okay, there's no selectivity. So for secondary alcohols, whoops, don't want to do a secondary alcohol yet, or don't want to do the ketone yet. Need the secondary alcohol. All of them. Okay, so you can even use the PCC and the Swern. I don't know why you would do that. They're kind of expensive, but they will all convert over to ketones. They'll all convert to ketones. All right. Well, what about tertiary alcohols? Yes, that's a trick question. No reaction. So remember, I say, ooh, does it have a hydrogen to give? Maybe I can put that on here. There needs to be color change. Okay, there would have to be a hydrogen connected to the carbon that has the OH group. Okay, no hydrogen. And so there's no hydrogen to give up. So you cannot oxidize a tertiary alcohol because that carbon already has its 4 bonds taken care of. All right, last but not least, what about those benzyl groups? Again, haven't really done much with benzene, but it's a good time to see what they will do. All right, if you have a benzyl and you use one of these strong, you're going to make it into a carboxylic acid. So you would get benzoic acid. All right, so PCC and Swern wouldn't do that, but the others will take a benzyl location and it will go all the way to a carboxylic acid. Then I give you some problems here. So give the products for a strong chromium reagent and a selective one. So we'll just do the first one together. We have cyclohexanol. If we use a strong, we're going to get cyclohexanone. If we use a selective, PCC or Swern, we're also going to get cyclohexanone. All right, so I give you just a few to practice with right there. All right, let's go to our next metal, which is manganese. And manganese is in the +7 oxidation state. And a long time ago in general chemistry, remember the further away from zero you go, the more reactive it is. And so we're dealing with a +6 and a +7. So manganese and chromium, they're very strong oxidizing agents. And the manganese that we're going to play with is potassium permanganate, which is KMnO4, and it looks something like this. Okay, so there's your potassium permanganate. We usually control it with some kind of temperature. Now, I say that tongue in cheek because really it is hard to control things with just temperature, but on paper it looks great. And it's generally done under basic conditions. So KMnO4 OH, might put some water right there. Okay, that will be something very typical that you see. Now, KMnO4 will just oxidize until it cannot oxidize any further. And that's the reason that we pretend to control it with any kind of a temperature. And so the first thing that we're going to play with is dihydroxylation. Okay, dihydroxylation. That is two OH groups. Okay, and they tend to be vicinal. Not tend to be, they have to be vicinal. Okay, so there's two vicinal OHs, and they have to be syn because they go on at the same time. And a generic mechanism looks like this. We have, we'll just do a generic alkene right there. So MN, if you will, it's just this nice concerted reaction. Do do, and then that's attached. Okay, this is not an exact mechanism, just a visual. And then that's where we have the OH and the water come into play, and it cleaves those bonds. Okay, now the key is they came on together, so they are on the same side. That is syn dihydroxylation. Okay, syn dihydroxylation. So technically, if we want it to stop there, okay, now what does cold mean? It just depends on the specific. So remember, in my world, if I don't say anything, it's 25 degrees. If I say cold, it's colder than that. And if I say hot, it's warmer than that. But we're talking pretty cold, 0 degrees, if we can get it, maybe even a little colder. Okay, liquid nitrogen sometimes works nicely on this one. That is dihydroxylation. Well, what happens if I don't control it with temperature, or I heat it up, or I actually try and control it with temperature, but I'm trying to go to the completely oxidized state? You go one step further, and it will literally cleave through that bond after it dihydroxylates, and you are left with, you know what, I'll just start fresh here. You're going to cleave through both of the bonds. I like to redraw the backbone. Now remember, when we were doing ozonolysis, we would stop right there, okay, because it was selective with an alkene. But this one is not selective, so we're going to go all the way to carboxylic acids. And there's your two products. And then don't forget this one, because it was on the end by itself, could go off as CO2. Draw it a little prettier. And that is called oxidative cleavage, because you're literally cleaving through the entire bond. Ooh, very, 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 very powerful. Nope, wrong. All right. So we have seen what happens with our alkenes. Okay. Well, how in the world could you get a ketone? For this example, you know what? Let's do this one. Remember, you can't stop at the aldehyde stage. When the world, yeah, hydroxide, H2O. Add a little heat. We're going to cleave right there. And 1, 2, 3, 4, 5, 6. And this one, okay, that one is that one. Oh, that's how. Because it doesn't have a hydrogen to give, it's stuck at the ketone state. But the other side, 1, 2, 3, 4, 5, and 6, will turn into a carboxylic acid. So it's not really anything special, except the starting material created the ketone. All right. Well, if it can cleave through the alkenes so nicely, can it cleave through the alkynes? And the answer is definitely. And we're going to have the same thing happen if it's terminal. And this one, I really don't care about the temperature. It's never going to do a dihydroxylation. It's only going to cleave. Whoops, that's a 2. Cleave, 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 cleave. Draw the same backbone with that missing and add. Because remember, you're cleaving through all 3. And so you have to replace all 3 bonds, and that is the carboxylic acids. And the only thing that you need to be aware of is that was a terminal one. So again, that can come off as CO2. All right. Well, what happens? Let me see. Go back up here. What if I use this potassium permanganate with primary alcohols and aldehydes? Okay, it's just like before. It is very strong and it will not stop. So they will both completely oxidize up to the carboxylic acid. Hey, what about your secondary alcohols? Okay, just like before, it has to stop at the ketone because there's no hydrogen to give. And of course, tertiaries aren't going to oxidize. Well, what about your benzyl groups? Potassium permanganate is probably the strongest one that we ever play with in the lab. And it's nice and purple too. Okay, and then your benzyl group will also go all the way up to a carboxylic acid, and then that one specifically is called benzoic acid. Oh, look, I give you a whole bunch of examples right here. So the difference is you're going to show hot and you're going to show cold, but some of them don't matter. Specifically, like the alkynes, hot and cold would give you the same product, but some of them it does matter. So let's take this one. Wow, they're all pretty basic. Let's take butanal. So 1, 2, 3, 4. All right, what is going to happen if you do KMNO4, and then of course it's basic and it's water. Now in this case, it doesn't matter whether it's cold or hot. Cold or hot helps with oxidative cleavage. So it doesn't matter, and it's going to go to, I didn't leave enough space. One, two, three, 4. Okay, hot or cold. Okay, so I give you a few of those. Now let's go to just a few selective ones. Osmium is a very interesting element, and osmium tetroxide looks just like that KMNO4, although it's not ionic, but it's going to do pretty much the same thing. But once it's attached, water isn't going to take it off. You're going to have to do a second step, which is sodium bisulfite, or you can use catalytic amounts of something called NMO, but this is the one I always use. Oh, well, what's so interesting about it? Well, osmium actually will coat your eyeballs. So you don't, I mean, you don't want to get manganese on your skin either, but osmium actually will, kind of pool into your fatty tissue and then it goes to your optic area and it'll coat your eyes. So this is not something you want to play with unless you have to. And so the osmium is more selective. And usually the more selective things are the more dangerous ones. So what are we going to do with it? There's only the the one reaction. It's going to take our alkenes and it's going to do the dihydroxylation, but it's going to stop. You don't have to worry about it going on and cleaving. And that's the power of it. But it does take 2 steps. So it's going to add on just like before. Let's see. There's going to be a little cyclic action going there. And so that's the stage that it'll stop at. All right, syn addition. So it's going to do the exact same thing as the KMNO4, but it's selective because it will not go further into oxidative cleavage. Now, I also included silver right here because silver is just a natural oxidizing agent. And oh, look, only a +1. Oh, didn't point this out. A +8 oxidation state. Okay, now the silver here, whoa, is only playing with a +1. So again, not as strong, but we can take that and use the lack of power for our purposes. So silver 1 oxide, which is AgD2O. Now the one that we use most often in lab is called Tollens reagent, which takes the silver and puts it into the ammonia and it makes a silver ammonia complex. And we know this as the silver mirror test because when you put it in your test tube, it literally coats the inside with silver and you can't get it off. So this was one of our qualitative reagent tests last semester. Hey, if you have an aldehyde, it will convert to a carboxylic acid and it will plate the silver out. Again, it's fairly selective. It's not very strong. So the only reagents that we played with were the aldehydes. So we took the aldehyde, we took I usually just write the word Tollens, silver and ammonia, and you're going to get the carboxylic acid and silver solid and silver solid. So again, not so useful for synthesis, but it's a great visual if you're testing and you want to see if you have an aldehyde. We actually used sugar. We used I think we tried sucrose, but we also had glucose, and that's what we put in here. All right, those are your metal reagents. Now, there are 3 different types of practice problems here at the bottom. I'm going to jump over to the whiteboard. All right, your problems are going to come in 3 forms. I will give you the reactants and the conditions. Yeah, I'm going to say and right there. You're going to give me the products. Okay, that's the first type. Pretty straightforward. The second type, I'm going to give you the reactant. Okay, now I have to be careful about saying reactant. Substrate is probably a better term, like we used in SN1 and SN2, but the conditions are missing. And remember that that means what's above and below the reaction arrow. Okay, so I'm going to give you the reactant and the products, and you're going to give me the conditions. Then last but not least, I am going to give you, okay, just the products or the products and the conditions, and you'll tell me what you started with. This is often called retrosynthetic analysis. Basically, if I say, I would like a primary alcohol, okay, how many ways do I know to make primary alcohols? And you can work backwards and say, okay, well, if I had an alcohol, I could have done that from a ketone. That's just working backwards. That's what retrosynthetic analysis means. So those are the three. I consider this one the easiest, this one the second, and then this one, I'm not going to put hard right there. I'm going to put the third hardest. All right, so those are the variations that we have. And share. This is also on. Oh, I'm not sure you're seeing that. Let me try that again. All right, this is also on your reference sheet. So everything that I do right here, I've put into words. And granted, when it's in words, it's not as easy. You know, a picture's worth 1,000 words. But when you're doing these reactions on your own, you can at least go back and say, how did she do that? Okay, so if I give you the reactants and the reagents, okay, so that means the conditions. Here's the steps that I'm going to go through. Okay, I'm going to use some terms called recognize or mechanize. Here's if I give you the products and the reagents. And where's the third? The reactants and the reagents. Oh, the products and the reagents. And then the last one is the retro. So these are the first two. These are the first two. So you can always come back. This is on your reference page. All right. And sometimes I'm not sure if that switches, so I'll stop and then I will share again. All right, so question number 8. This one, basically, there's definitely not enough room, by the way. This one is basically you going backwards and say, how could I make an alkane? Now I'm limiting it for this for only oxidation and reduction. So if I was just to do it off the top of my head, I would say hydrogenation of alkenes and alkynes. Okay. You will probably go back and look at your reference sheet at the oxidizing products and the reduction products, and you would list every way there is to make an alkane. Well, how many ways can you make cis or Z alkenes? How can you make the trans or E alkenes? This is basically the retro. This is the hardest because you either have to know it off the top of your head or you have to know where to look, which luckily you do have your reference sheets. All right. I don't know why I put that problem first. Oh, yes, I do, because I wanted you to go look and get familiar with your reactions. Okay, now the second one, if you'll notice, in this case, I am asking you for the products. So this is the technically easiest way to go about it. All right, and here's the steps. Step number 1, identify the functional group of your reactant. Okay, this is an alkene. Now, right now, you have a choice. Do you want to kind of go through the file that just opened up in your head and go, okay, what do alkenes do? You might be getting to the point that there is so many reactions that that is not helpful, but sometimes it's nice to just make a short list. Okay, what do alkenes like to do? Well, alkenes like to add because they have pi bonds, and then of course, redox, but they specifically like to add. All right, so that's the first part. The second part is to look at your conditions. What is that condition? This is where I say you can either recognize it, okay, or you can mechanize it. This one means I have no idea what I'm doing, and I will pick out the nucleophile and go for the electrophile. And hopefully along the way, you realize, oh, that's what I'm supposed to be doing. I do not like things to be memorization, but you are going to get to the point where you're going to have to start recognizing some of these reactions because I haven't given you mechanisms on all of them. And so sometimes I do rely on that. Okay, so let's recognize or mechanize. I recognize this as a peroxy acid. All right, what do peroxy acids do to alkenes? Oh, this is epoxidation. And then you go ahead and do the products. And don't forget about stereochemistry, regiochemistry. If you make two of the same type of functional group, give me major, give me minor. All right, but there's the two key components. Let's do another one. Let's do, you know what? Let's do L. Okay, step number one, identify the functional group. Okay, so this is an amide. All right, what can amides do? You've only ever seen one reaction, and that's oxidation and reduction. All right, now look at your reagents or your conditions. Your dibal, what was that? Let me see. Okay, now if it doesn't immediately come to mind, this is supposed to jump at you as a selective hydride. Oh, this is reduction, and it's a very selective reduction. And so this one's going to make an aldehyde. All right. I know that looks probably easier than it really is, but don't just jump in. Take the time to talk about each one of these. Okay, this is my reagent or my reactant. This is what it could do. Don't make an exhaustive list, but kind of have an idea of what it could do. Here's my conditions or my reagents. What is it trying to tell me to do? And then go on and do your products. And then it's always nice to go back and say, hey, what am I doing? Am I doing addition, substitution? Am I doing rearrangement? Now, this handout, of course, is on Redox, so you don't really need to do that, but it is a nice visual. For instance, this one specifically is syn addition. Well, it's also oxidation. Yes, all oxidations fall under one of the big four. All reductions fall under one of the big four. It just depends on which terminology you want to use. All right, so there is you tell me the products. And last but not least, here's the I gave you the starting material and I gave you the product, and you're going to have to tell me how to get between them. Let's choose, you know what? Let's choose M. All right, what functional group do I have? In this case, you tell me the functional group of both the reactant and the product. Now, if there's anything special about that functional group, you need to put that in. So for instance, this one has to be happens to be a cis alkene. If it's an alcohol, don't just say alcohol. Is it primary? Is it secondary? Is it tertiary? Is it a Markovnikov? Put some kind of identifying factor with it. And so my question for this one is, how in the world can I get from an alkyne to a cis alkene? Now, you will either recognize it or have to mechanize it. But in this case, recognizing really becomes easier. And if all else fails, you'd go to your reference sheet. Oh, but this will use hydrogenation but I can't let the hydrogenation complete, so I need to use a poisoned catalyst, and that would be Lindler or P2. I kind of like these. Hey, what's happening here? I have a trans alkene. Oh ho ho! I added oxygens, so it's oxidative. Oh, and I cleaved it. So I have oxidative cleavage of an alkene. Oh ho! Was it selective or did it go all the way around? That is an aldehyde and that is an aldehyde, so it was selective. Oxidative cleavage. So how do you selectively cleave an alkene? Hmm. KMNO4. KMNO4 goes all the way up to carboxylic acid. What was that other one? If it's not right off the top of your head, you can go back to the sheets. But this one is ozonolysis. And then we could put the actual conditions. All right. I hope that kind of gives you an idea of how to work it out. There are a lot of problems on here. There are a lot of problems, but I tried to give you an example of each one. You're going to go until you're comfortable. Of course, trying all of the problems would be the best case scenario, but that would take forever. And I'm visualizing a movie right now. Forever. The Sandlot. All right, that ends our discussion on oxidation and reduction reactions. So until next time, jolly out.